Alright everyone, if you've ever played Astroneer, you're aware of the planet Desolo. It's basically a circle with weird circles inside that are brown. Just assume this is brown. This is brown. Definitely, guys, come on. You see it, it's brown. What are you talking about? But basically, me and the boys decided, hold on, what if we use something in the game to completely destroy Desolo? And we came up with two options. I'm only going to be considering option 2 today. We're not going to go over the time or anything, but we are going to go over how much it actually is going to take. But basically, we can either use the drill gun that you have pre-equipped, which would cost almost nothing, especially in creative mode, or we could use explosives. Now, we're going to be looking at explosives today, obviously. Why wouldn't we be looking at explosives? So, it begs me, I beg the question, how much dynamite does it take to blow up Desolo? How much would it take? And obviously, that's not... Thank you. Obviously, that's a question that'll take math, because that's basically a two-part question. Well, three-part. Part 1, find volume of one dynamite explosion. 2, find volume of Desolo. 3, divide V of D by V of D. V of 1D. You know, same thing. That is not very close, but that's just what we're gonna have to... So, let's find the volume of one dynamite explosion first. Now, obviously, that's a problem. Because, well, there's not really a unit of measurement in Astroneer. There's no meters, feet, inches, refrigerators. And sure, we could use the fact that, you know, an Astroneer would probably be 6 feet tall, but we don't know that because this takes place in like the 27th century, I think. So humans could be 8 feet tall at average now. They could be 2 feet tall on average now because they found out that, hey, being smaller means we use up less resources and have more world and land. Who knows? Maybe they've invented shrink rays. I have no idea. So we can't use any of that. So what we're going to use is the terrain tool. terrain tool constraints, or T for short. We're going to call it T. What's a terrain tool constraint? Basically, in creative mode in Astroneer, if you press Y while using your drill gun, you get a big menu that allows you to control the speed, size, range, and color of your gun, or the terrain tool. So, if we take this range, and these give actual numbers, it's a slider, each one has a slider, speed, we don't need that. But size goes from like 50 or something to 700. Range goes from 3,500 to 8,500. Things. So, we're going to call all of these measurements T. But we can't, because we know what range is talking about. Range is very obviously referring to the line from the player to the very edge of where they can build. They can't build past this. Of course, it's a circle, but still, same thing. It's a line, and all those in the circle would be lines, so it doesn't really matter. So, we can minimize this to 3,500. But we need to find the volume of a dynamite explosion. Let's step it back a bit. So if we have a large piece of land here, we dig a little hole, drop a dynamite in it, light it, and let's say, and we have a hole that is much smaller than 3,500. That's a problem, isn't it? Sure, we can find the radius by drawing two lines that are approximately at the center to find that this right here is this, and that this is the radius. So, how do we find these lines if they're much less than the 3,500 we're given? Well, we need to find the size. Well, how do we do that? The size controls how big your gun is. Larger the size, larger the circle. But hold on. That's true with 4 different aspects of the circle. Granted, 2 of them are the same, just one's double the other. But it's very important for us to know which one this is, so that we can use the circle tool to just make 2 tiny circles, so that we can actually measure how long this line is in terms of the circle's diameters. So we need to find the diameter of a circle with size 700. Seems like it would be easy, right? It's just 700, right? Well, not so fast. Size could be referring to radius, diameter, circumference, or area. Those all can be used to determine the size of a circle. So which one is it? To do that, we're going to have to put circles on this line, right here. And when we put size 700 circles on this line, we get 3 circles with a tiny bit of extra. Which we can't measure with circles. It's way too small. But basically, 3 circles means that, so 3500 divided by 3 equals 1500 is the diameter of one of these circles. About. Well, what does that fit with? Well, let's take for a second that 700 is referring to radius. That means the diameter would be 1400, which means that can account for 300 t here, right? So let's go. This is good. We're figuring things out now. Which means this actually goes from like 100 t to 1400 t. Nice. You know, circumference 14. You know, we don't need the area. We're never going to need the area of the circle. We're going to need the volume of this radius here. So, what's the volume? Well, we have a circle that perfectly fits it. It's this volume that has a size of 520, which means that the size, no, it is 520, which means the diameter is equal to 1040, and the diameter of this circle is the radius of this circle. Make sense? I hope it does. So we have the radius of one dynamite is equal to 1040. Easy enough, right? Let's put a T there. Now, here's the deal. We can plug this into the equation. V equals 4/3 pi r cubed. We plug this in for 1040 t, and we plug pi 3.14 in for pi. Then we get the number 1,824,864,000 t cubed. And we're only a third of the way done. Alrighty then. 2. So, now, 2. Find V of Desolo, which we can do this actually even easier than we did the dynamite. It'd be more time consuming, but it's a whole lot easier. Since we know that the range, we can set the range to 8,500, which, let's just say that's about there. And then we can draw a straight line into the core of the planet. That's way too big. The core of the planet. We got this. So we want to go to here. Now, to get to here is a tad bit time consuming, but we get that we have we have 6 different lines that are worth 8,500 before things get complicated. So we have 6 plus. Then we can use the. Then what I did, I would recommend doing this if you're gonna measure other planets, is I drew this and I filled this in with a different color of material. This material I made just black or something. And then I used circles to measure that distance. And that is about 700, 1400, because 700 is just the size, times 6. And then we had a tiny area that was 360. Add all this together, we get, I believe it was 597. $24. Okay. So it ends in 4. I believe we got something close to that. I could be wrong. Actually, let me check. Nope, I was right. Wait, no, there's. That's a lot smaller than it should be. This is the number we get 59,760. You know what's a lot easier to work with than 59,760? 60,000. This never existed. There was never a margin error. Nothing at all happened. We can all go back to our piece knowing that the radius of Desolo is 60,000. Plug that into the equation, and we get, so 4 thirds, 3.14, times 60,000 to the power 3, we get exactly 904. Yeah, 9.0432 E14. What's E? Well, E basically means times 10 to the power of the next number. So basically, in this case, it's 9 times 10 to the power 14, which is quite a bit, as rumor may have it. This ends up being because E9 is a billion. 9 zeros. No, yeah, 1 billion. So this is so 12 is quadrillion. It's a lot, okay? It doesn't really matter. But that's still not it. We're only 2/3 of the way done. Now comes the most difficult part. I even messed it up in practice, see? You have to take this number and divide this number into it, which is very difficult. What we have to do is you take TI-84 plus CE, you take the number we just got, hit the divide button, and enter in this number. I did that wrong. 1 second. Oh wait, no, you do divide it the other way. No, I did that right. Never mind, I'm bad. Okay. I didn't find the volume. I'm dumb. Ignore that. It's not true. It is fake news. I forgot to multiply that by 4/3 3.14. I think. Who knows? But it's actually I completely forgot to multiply that. That's okay. So we instead divide this number by that. And we get the legendary number x. Now I bet you're wondering what x is. And no, I'm not going to make you actually divide. It's 192,023.2135. So because we can't have half a piece of dynamite, put a 4 there. Now, this is the best we can get. Not really. There's a problem here. That means that number implies that we put 192 separate pieces of dynamite into the core of the planet. Like, we just completely filled it, probably filled like 10, filled the entire thing with it. The entire core is just dynamite, which, makes sense. Problem. I don't know about you. You might be Bill Gates. I don't know. Bill Gates could be watching my video. But my PC can't handle calculating gravity for 192,000 separate pieces of dynamite. That's not something I can do. I can't. So, gonna have to divide it into pieces. Let's keep this number up here. So, in a perfect world, we have that amount. Now, but contrary to popular belief, we don't live in a perfect world. So that's not going to help us. So, obviously, we're going to have to divide the sphere into more spheres. You saw nothing. I'm going to pretend that hit. You know, they all touch at one point. Very tinily, maybe. Who knows if that's even possible. Actually, it's not. We have 4 things, which make a nice little square. Actually, not really. So, we have a square with 4 circles inside of it. Since, you know, let's divide this up into squares with circles in them. Now, let's do an example with this one. Has a radius 1. And this circle has an area 1. Wait, these are spheres. Radius 1. So, the cube will equal 8 units cubed. The sphere, because it's 4 thirds pi r cubed, is just 4 thirds pi, or or 4.1887, which, let's put a 9 there, which, that's a whole lot less than that, isn't it? But it makes sense, doesn't it? If you have, let's draw this. And we have a shape that, even if we shade all that in, that's an entire 4th of it. Probably I'm blocking it for you, but you have that, 1/4 of that, even though it goes all the way to the bottom of that, barely covers anything, really. We have and we end up with something that kind of looks like this. But 3-dimensionally. Let me try to put this in perspective. See? We get something like this, and this is actually huge, because what it does is it goes up, slowly getting smaller and smaller until it disappears for like a tiny piece, and then does it on the opposite side, which means there is about half of the cube remaining if you put a sphere inside of it and get rid of all that. That is how much there is. About half. So, if we have not including these spaces. And, of course, not this. And, of course, we're accounting for all this. We're leaving behind, with the exact same amount of dynamite, because we just divide by 4 to get these. Actually, 8, because we would need 8, so, you know. So we get that each of these is 24,003, and it, in total, this only covers up half of this cube. Now, we actually know how big the cube is, because this is a radius. So, because this is a diagonal, we can draw this here to get a 45, 45, 90 triangle. This is a straight angle. This is 45 degrees, and because triangles, this is 45 degrees. And for any of you who do not know, Pythagoras' theorem actually makes it a lot easier. S square root 2. Why does this happen? It's because because a squared plus b squared equals c squared, that if we have s squared plus s squared equals x squared, you get 2s squared equals x squared. We take the square root of this, and we get that x equals s square root 2, because the square root of s squared is s, and the square root of 2 is the square root of 2. So, you know, nice little geometry trick. So that means, since we know that this we know that this is 30,000 square root 2, because s over square root 2, let's use x actually, is equal to 1/2 s square root 2. So, next, square root of 2. These are the same thing, which makes dividing by roots a lot easier. You know, we could have n here, same thing. I mean, obviously it would be 1 over n as well. That's important. Okay. But basically, we have that one side is this, the whole square is this. So, to get the cube, well, this whole side equal to this, to get the whole cube, we cube that, and we get, well, the power of 3 is 6.11 E 14. Big number. Again, we're moving up the numbers each time. But this, when compared to the whole amount, which is about 9.04 E14, this square only covers about 2/3, this whole thing. But we take this and we take half of it, basically. We get 3.06, because that's the closest thing we get. E14 is what is being blown up. About a little more. This is what's here. This is what's left over. Maybe a little less. Add that to the amount we didn't even blow up. Let's start using real numbers. So 904, well, it's not real, it's real numbers, but 904 minus 611 is 293. 293 survives 2.93 E14. In addition to this. So 293 plus 306 is 599. So we're going to do 6E14 about, because it's just so nice and close, and margin of error should either take us out or back up, so it doesn't really matter what number we use here, and making it as convenient as possible is what we want to do. So this is the amount left when using this amount of dynamite in any other way than what we have. Yikes, right? A lot is missing here. In fact, less than a third was removed. Geez. But here's the good thing. Because technically we can place these spheres anywhere we want, let's take all the remaining land and clump it into one ball, which is the size of this. So we have this. But let's step back a minute. In fact, let's step back a lot, actually. Alright, so this is what's left. So, what we do is we take the radius of one dynamite, which again is this big boy, and we take this and divide it by this and see if we get anything that isn't huge that we can actually use, because if we can actually use this, we can put all the dynamite in the core, blow it all up at once. So, let's use red now, I guess. Red's a cool color. Alright. So we take 6E14 divide by 47094300613, and we get 127,133.9806. So we add this to that. good world. 127,134 plus 192,024 is equal to 319,158, which is, it just gets increasingly worse as you realize that you would have to do all that again and again and again and again. And there's no real way to get it less and less and less laggy. But let's do some quick math. So if we divide 192,024 by 127,134, we get that it needed to switch them. 127,134 divided by 192,024, we get that it is 0.6. So we get that the ratio between these is 0.66207 ... Let's just use 0.66 because it's cool. So what we have now is, since it would have taken this much to delete the whole world, it would take only take 83,842 to separate it into, okay, so then because it's 0.66 to 4E14. So this is what is required to blow up this. So with n times, we're going to make a nice little formula for this. In fact, we're going to make two. One to determine how much planet we have left, and one to determine how much dynamite we'll need to blow the whole thing up. And one for in total. Actually, the dynamite in total is what we're going to be looking for. So we have exponential growth. Which exponential growth is, so exponential growth is x equals a 1 plus r to the power t. Actually, no. This is y. So that's the exponential growth, but what do we substitute in? Well, a is the initial, it's the initial amount, so we would only need, geez, I'm not sure this is right, but, wait, no, it is, yeah, it is. Okay, so, 1 second. Alright, so we have that y, so that a, so we have y equals 192,024, 1 plus 0.66 to the power x. That is the formula we need to display this. Now, let's actually graph that formula. Actually, let's not. This is the formula to detect how much dynamite in total it is going to take. But what if we want to know how much land is left? Well, it's pretty basically the same principle. We start with 9.04, go down to 6, go down to 6, then 4, and it does the exact same thing. It goes down, though. So, instead, for this equation, we're going to have y equals 9.04 e 14 times 0.33 to the power of x. If I'm correct. Because this is 1/3. No, this would be 6, right? Yeah. Because that is 2/3 times itself a few times, and we get this. So, what is going to be the ideal amount of land? Because obviously my computer probably isn't going to be able to handle 83,000 about as well, about like at all how it's going to handle 19,000. Let's try to get this number under 20,000. So because we have a correlation between the size and how much dynamite there is, and it is this number, we need to get a size. So if we multiply this number by 20,000, we'll get about as much land that we'll have left, which will cause us to be able to actually handle it at a reasonable size. 20,000, still a huge number. Am I gonna do that all at once? Maybe. I might try it, okay? But I am not gonna blow up the whole thing. Let's be honest, this would take hours. But what we do is we take 4,709,430,613, multiply it by 20,000, and we get that we would need there only to be 9.42 E13 for this to work. And obviously, you can see how it gets smaller and smaller and smaller over time. It'll eventually get down to here. We won't ever actually get to this number exactly. We'll get to things lower than it and higher than it, but x would have to be a weird number for it to actually do anything. So I'm going to plug this formula into my calculator. We're actually going to plug both of them in. So we get 9.04 E14 times 0.66 to the power of x. Then we take the other formula, which is 192,024, 1.66 to the power of x. What we get, let's see if, alright, here's the deal. You can see that. We need to find the point where these intersect. Wait, do we? Where they intersect. They don't intersect. Never mind. We need to find where this is equal to 20,000. We need to go to where that equals that. Need to zoom in a lot. Why is it up there? In fact, let's just do zoom standard. These are huge numbers, actually. Like, I don't know why I'm using these numbers at all. To be honest, it's probably going to crash my calculator. So we need to find where this equation goes down to the y being equal to that, which comes approximately at 5. So we would need to do this 6 times. So we do 6, find that it's pretty good. Find 6 here, and find that that plugging 6 right here gets you the ginormous number in a reasonable-ish world. You would get the number 4,017,946 dynamite to blow up the moon. So needless to say, I think this number is much better than what this number is. It'd probably be less work for me to become a billionaire and buy a computer that can process this amount than it would be to actually place and get all that TNT, blow it up, do all the filtration and stuff. And that's not even telling you that you have to do that 8 times 6. You have to do that 48. You have to do 48 balls of bombs, which blow up a fourth of the planet. Not a fourth. A 16th of the planet, which is huge. And if we could have square explosions and square planets, it would not take anything. It would take this amount. But yeah. So we have a formula. Let's keep everything that we've gotten. We have If your computer can handle 20,000 dynamite, it would take 4,017,948 dynamite to blow up Desolo. If your computer is made out of enchanted gold, runs off of only the network of God himself, and manages not to crash, it would take 100, I keep calling it 192,024. So, that is how much dynamite it takes to blow up the Desolo. The easiest answer is 192,024. So, I guess if you like this video, subscribe. If you didn't like it, I don't know. I mean, that's cool, I guess. Not everyone has to like nuking the moon with literally millions of dynamite, but, you know. This is the best number I want to do. Anyways, subscribe.